All right, here is video solution for, my little pencil for 2004, number 1. If I were going to nominate a free response question for best free response question ever, I would seriously consider this one because it's just awesome. So here's the situation. There's a guy sitting on this ledge and gonna swing down and grab this lump of something, and then going to become a projectile holding onto the thing and land, I went too far, and land here at point D. And we're gonna figure out a bunch of stuff about that. Okay, so rope of length L, you can read through all that and derive expressions for each of the following in terms of these. Lots of times they give us just these things and say and fundamental constants. Here they're actually saying and G, so sometimes they do that, sometimes they don't. So how about the speed of the person just before the collision? So there's no friction or anything, so that means mechanical energy is going to be conserved from here to here. Anytime you have something that's changing its height, you should consider conservation of energy. So I'm going to actually write that out. Remember that you're trying to communicate with other human beings. So I'm going to say mechanical energy is conserved. There are other ways that you could say that. You could write delta ME is equal to 0 if you don't feel like writing out the words. But you should say something like this so it's clear what the work that you're going to do is based on, what concept you're using. So that means that the gravitational, what's that? Let's undo that. The gravitational potential energy at the top is equal to the kinetic energy at the bottom. So that's the mgh is equal to 1/2 mv squared. The m's cancel out. If you're going to cancel things out, you can do that. Just don't do it in a really messy way. You don't have to like scribble them out so they're impossible to see. And we're trying to solve for the v at the bottom. So v is equal to the square root of 2 g. And here the height is, since the person's holding onto this rope, this distance here is also L. So probably if I were doing this with pencil, I'm not doing it with pencil, but I have this handy little pen thingy that I can erase with. I think probably I should have made that an L. You could make that an H and then make the substitution later. But anyway, that's going to be the speed at the bottom. You can bet that you're going to see some version of that. Gravitational potential turns into velocity, turns into kinetic energy. Okay, how about the tension in the rope just before the collision with the object? So this person is in circular motion, not uniform circular motion, but because they're speeding up. But they are moving in circular motion, which means that there must be some unbalanced force toward the middle of the circle, and there must be that much of it. So let's see. What are the forces on them? At the bottom of the swing, the person has the force of gravity on them, of course. And then they must have a tension force here. Why did I draw the tension force bigger? Because there has to be unbalanced force toward the center of the circle. That is not negotiable. That has to happen anytime there's circular motion. And of course, gravity is still there. So the unbalanced force, the sum of all forces on the person, is this tension force minus mg. And the sum of all forces on something that's in circular motion must be this, toward the center. So that means I've got mv squared over, and now this is not R, this is L, just like above, and that's equal to T minus mg. That would probably get you 3 of the 4 points, but we know the v here, and so if I square the v, I just get 2gl. So let's see, that's m times 2gl. That's substituting from part A over L is equal to T minus mg. So let's see, those L's cancel out. So I have T is equal to 2mg, and then there's the minus mg, so I'd add that to the other side, so 3mg. I think it's, I'd have to go back and look at the scoring guide, but I think if you have these two forces being equal to each other, I think that's a big old 0 out of 4 for this part. Not recognizing that, or maybe it's 1 out of 4 for recognizing that there's two forces, but you don't get much if you don't realize that there's more force up toward the center of the circle. All right, how about the speed of the person and the object just after the collision? So collision, anytime we have a collision, that should make you think about the total change in momentum is 0, right? So that means momentum 4 is equal to momentum after, and this is like the total of those. You could put little sum signs in front of those. I don't think anybody's going to fuss too much as long as you have the idea. So the momentum before the collision, well, before the collision, there's the person, and the person has a mass of m1, right? Have I been using m1? Am I doing that right? Maybe I haven't. Let's see, person has a mass m1, so I should be very careful here. This needs to be an m1. I don't know how fussy they are about this, but it could very easily cost you a point because in this problem there's an m1 and an m2. So you got to stick with what their notation is. Here, you know, over in your work, your little force diagram, I don't think they're going to penalize you for that. And if something cancels out, you know, we still have the right answer there, but please be careful. All right, so m1 times the velocity of the person right before the collision is square root of 2gl, and the lump of the sack of rice or whatever it is not moving, so it doesn't have any momentum yet. And then after, the person and the sack are now basically effectively the same object, and we're looking for the velocity of them after the collision. So you could call that VF if you want. You could just call it V because we're not using V for something else. And that means that the speed of the person and the object just after the collision is equal to this. All right. How about the ratio of the kinetic energy of the person-object system before the collision and to after the collision? So setting up a ratio like this, what that means is we want to make a fraction, ratio of the kinetic energy of the person-object system before to person-object system after. Right? That's what we want to do. Okay, and we will just want to simplify that a little bit if we can. So let's see, kinetic energy of the person before, of the person-object system, well, only the person has velocity before. So that's 1/2 mass of the person times their velocity squared. And I'm just going to go, I don't know what to tell you about skipping this step or not. I think I should set a good example not skip this. And then this is that VF squared, right? All right, so simplifying that. I'm writing this out because I think probably they have a point for the doing 1/2 mv squared, like clearly showing that you know, oh, kinetic energy, that's 1/2 mv squared. All right, so let's simplify this. The 1/2s cancel out. I've got m1 for m1 plus m2. And then here I've got v squared. This v squared is the original square root of 2gl. So that's 2gl when I square that. And then the velocity afterwards is what we just found in part C. So that's this expression. I have m1 over m1 plus m2 times 2, oh, so that's squared, right? I'm squaring the whole thing right here, this thing, times 2gl. So what does that simplify to? The whole 2gls cancel out, and then I've got this times over 2 of those. So this whole thing cancels out 1 of those, and then I've got that left on the bottom. And since it's a fraction bottom, that's just going to flip it over. So that all simplifies to that. That is the ratio. If you're thinking like, oh, wait, I thought it was supposed to be a ratio like this, that's really like we don't really do ratios like that anymore. You can do it like that, and that's totally fine, and they would count that as correct. But when you see ratio, you think fraction. All right, and last part, what is the total horizontal displacement x of the person from position A until the person and object land in the water at point D? Guys, I'm making a video. I'll be done in about 2 minutes, okay? Thanks. So at that point, they become a projectile. So we have vertical, horizontal. It's super important to recognize that the initial launch of the person and sac is horizontal. So the initial velocity here in the vertical direction is 0. It's a horizontal launch. This is a favorite thing of the College Board. The acceleration is -g. The, let's see, the delta y, they're falling down another distance L, so that's -L. And we're interested in, we're going to need to find the time here. So let's go ahead and do that. So let's see. I'm going to use delta y is equal to 1/2 at squared plus vit, but the vi is 0. You could write that plus vit. That's going to be 0. Okay, so that's minus L is equal to minus g over 2 times t squared. So t is equal to the square root of 2L over G. And that was worth, I remember in the scoring guide, that's worth some points right there to get that time. All right, in the horizontal direction, the launch velocity, let's see, I think that's our answer from part C, right? That's the launch velocity of the person and sac after the collision. So got m1 over m1 plus m2 times the square root of 2gl. And now I know what the time is. It's the square root of 2L over G. So I'm going to find the delta x. So delta x is just equal to the product of those, because that's how constant velocity works. So let's see, that's m1 over m1 plus m2 times the square root of 2 GL. Oops, it'll just be an L there. And when you multiply square roots together, you can just put it all under one square root. So let's see. I could put L over G. I could do that. Right? Okay. So let's simplify that a little bit. Delta X is equal to M1 over M1 plus M2. And then what's going on under here? 2 times 2 under a square root sign, so that's just a 2 on the outside. L squared is under the square root sign, so that's an L, and the G's cancel out, so just 2L. So that is delta X, and that would get you 3 out of 4 points on this part. But if you look back at the original picture, what we just found, we found delta X, which would be, or what we called delta X, which would be this distance, right? That's how far they went after they became a projectile. But in fact, this distance L, like they're asking for the total distance from here. So we have to add L onto that. So the total distance, or the total horizontal distance, what do they ask for here? Total horizontal displacement, is equal to M1 plus M2 times 2L plus another L. And that is it. Greatest problem ever.